there it is. Okay. So welcome everybody to the November 2022 Astronomy Fundamentals meeting of the month. I'm Connor Justice, I'm the organizer. I see a couple of new faces on here. For those who are unfamiliar with how this meeting normally works, it's two presentations that are given out by members of the group. One, earlier this year, we had completed our long-running series on constellations of the month. Finally made it through all 88. We've kind of transitioned into doing a spotlight on astronomers of note. So tonight, Stephen Ferris will be presenting on Gerard Kuiper. After that, we will have, I will be giving the main topic, which unfortunately will be probably pretty quick, on meteor showers. Given Q4 of every year, there's almost a meteor shower going on every other week that has a peak period every other week. So it seemed like a good topic to dive into a little bit with all that, because we hadn't done that before. So for next month, I will be unavailable to host this meeting. So Doug and Stephen, and Pete, if I can chat with you guys for a little bit at the end of this meeting to see if we should still have next month's meeting, or that sort of stuff once we get through tonight. Don't want to keep everyone around through that discussion. No, all right. So without further ado, Stephen, I need to make you a co-host so that you can present. There you go. Take it away.
All right, I'm going to go ahead and share screens, if this will let me, and then go get my presentation. Let me do this. There we go. That should be it. And then we'll go to slideshow, if I can get this to cooperate, and from beginning. All right, so I'm going to, tonight we're presenting, so the last couple of months we were doing ancient astronomers. This is an astronomer who's been much more recent. This is just meant to be a very general survey of the stuff that he did. One of the things that I found in investigating this is he has quite a legacy behind him that could take hours to explain. But I wanted to just go over what the highlights of his career were. Normally I do a lot of pictures and the like. It's harder to do that with a biography, so this is kind of be a few walls of words, but we'll get through it. Gerard Kuiper was born in 1905 and lived until 1973. And he, as I'll talk a little bit about, is a slightly controversial character. Like a lot of scientists and astronomers of his generation, he could be a challenging character, but also a very inspirational character for the people who worked with him, in that he pioneered several things which are very critical. He's also a major figure to the University of Arizona, which I'm a part of. I'm not here officially representing the university, by the way. I just had that shirt on from today. I need to say that as a disclaimer, but the university, he was a major figure in developing our lunar and planetary lab, and later, at the very end of his career, the planetary sciences department. This is Kuiper, I believe, in the 60s. Other than that, I don't have a lot of other pictures to show, just some words and information. He was one of the founders of modern planetary science as a separate sub-branch of astronomy. So when Dr. Kuiper began his career, astronomy and planetary sciences were often interlinked much more than they are today. And especially for the 20 years between the discovery of Pluto and the rise of the space age, or World War II would be a better way to say that. There hadn't been a whole lot of stuff going on within planetary science. He was also noted as a pioneer in infrared astronomy. So today, infrared astronomy is a critical part of all of astronomy, but it's interesting that it had a lot of its roots in planetary science.
I assume that Stephen froze for everybody else.
I can't hear Stephen, and his picture's not moving.
Yeah, he might have had an internet connection, as he did briefly mention this before we started the recording. So we will give him a moment and hope that he rejoins. Sorry about this. I'm going to pause the recording while we wait for him to come back. So
Okay, so I don't know what's going on tonight. As far as I can tell, the internet's on my end is the one that's conking out, but I'll try and keep up with as best I can. Hopefully that doesn't happen again. So we were talking about, I'm going to screen share again. Hopefully is this where first thing you saw?
Yeah.
yes,
Okay.
you had just finished up with the infrared astronomy.
Okay, and then as I said, he was saying he predicted but did not discover the Kuiper belt. So he and as we'll talk about a little bit later in the lecture, he anticipated that the Kuiper belt was there, but it wasn't until 20 years after his death that the first confirmed objects were discovered. And there's a caveat there, but I don't want to go into that right now. A little bit closer to home, he was founded the Lunar and Planetary Laboratory at the University of Arizona, and the buildings is there that is we sometimes use in the springtime is named in his honor, the Kuiper Space Sciences Building. It was not originally known as that, but that's the name that it took on after his departure and death. He played a major role in the pre-Apollo reconnaissance of the moon. He was certainly not alone in that, but he was a major figure in that. And as I said, both the Kuiper Space Sciences and the Kuiper Telescope on Mount Graham are named in his honor. Let's see if this is working right. Okay. Just a very brief discussion of his birth and early life. He was born in, I do not know how to pronounce that, Tucson, North Holland, Netherlands, on December 7th, 1905. His father was a tailor, and he developed an early interest in astronomy. And according to some of the apocryphal information I was able to find, he apparently had very good vision as a youngster, which was one of the things that aided him in his astronomy interests. I don't know if that persisted throughout life, but that at least is a story that was said about him. He attended the Leiden University in the Netherlands. He completed his doctoral thesis in 1933. His thesis was actually about binary stars, not planets. So that was one of the things that is important, is that he started his career looking mostly at stars, not the planets themselves. What we now call planetary science was still very much linked with astronomy at that point. It was not necessarily a separate, distinct field. Of course, today it is still considered part of astronomy, but it's considered a separate branch with its own subdivision within the American Astronomical Society, and is often treated in some colleges, such as ours, as a separate department. Astronomers could study the solar system and vice versa. Solar system enthusiasts were astronomers. Kuiper was originally a stellar astronomer, not necessarily focused on planets. And upon receiving his doctorate, he moved to California to work at the Lick Observatory as a postdoc. 2 years later, in 1935, he moved to the Harvard College Observatory, where he met his future wife, and that was for a postdoc as well. In 1937, I'm sorry, I'm mixing up my numbers. In 1937, he moved to Yerkes Observatory and the University of Chicago. Although he's closely associated with the University of Arizona today, he actually spent the largest section of his career working at the University of Chicago, obviously in Chicago and with the observatory there. From 1947 to 1949, he was the director of the McDonald Observatory in Texas. At that point, McDonald Observatory was jointly run by the University of Chicago and by the University of Texas. In the 1960s, at the beginning of the space race, he moved to Tucson to found the Lunar and Planetary Lab at the University of Arizona. So his early discoveries prior to to coming to Arizona, where the atmosphere of Titan, which he discovered in 1943, the winter of 1943 and 44, while he was on leave from war service, and we'll talk in a minute about that, and while collecting observations of high parallax stars and white dwarfs. He had a bunch of program stars that he was working on. He ran out of those, and he noticed that several of the planets were lined up in a convenient spot of the sky to look at that particular point, to look at in terms of, and their moons were also visible. And he turned the spectrograph on the moons of Jupiter and Saturn. And he also discovered the Uranian moons of Miranda and the Neptune moon of Nereid. I'm messing up that name, but so one of Kuiper's greatest contributions was his work on infrared detectors, and there's kind of detectors, and there's kind of a cool story that goes on with that. Kuiper was fluent in several major European languages. Like many of the leading scientists at the time, he had immigrated to the United States well prior to World War II, obviously, unlike many of the other scientists who had to escape Hitler. But he was fluent in German, French, and Dutch, obviously, and English, which made him of use to the war effort because he could serve as a translator and was relatively familiar with the cultures of Europe and like. And so he spent a good deal of World War II working for the US government at the Harvard Radio Research Laboratory, but they recruited him to go to Europe directly, specifically towards the end of the war, specifically to examine intercepts dealing with the suspected German program dealing with an atomic bomb. The Americans at that point were well engaged into the Manhattan Project, were also concerned that the Germans had a program going on. As it turned out later on, they were had much less advanced than we thought they were. But Kuiper was one of many people who was recruited to do some of the scientific looking at that because he could also speak German and read and write in German. He was, interesting anecdote, he was personally involved with rescuing and more like capturing physicist Max Planck, who was considered one of the fathers of quantum physics. He basically received an intercept that Planck was about to be captured by the Soviets at the end of the war. And so according to the story, he requisitioned a Jeep, drove out deep into German and Russian occupied territory, found Planck, grabbed him, put him on the Jeep, and drove him back to Allied territory. He also, the most important thing to his later scientific career was he, from captured German and Austrian scientists and intercepts, he learned that the Germans had been making significant advances in developing infrared detectors. Now, the Germans were not interested in infrared astronomy at that point. They were going to use these things as guidance systems for their V-1 rockets, which were, of course, being used to attack Great Britain at that point as the last-ditch effort to try and turn the war around. And that gave him a certain advantage because, unlike scientists on the mainland, who were not aware of these things, he knew that these things were in existence. He did not invent them himself. That's an important point. He just knew that the Germans were working on them, and he later learned that the Americans were also working on them for similar purposes. The German devices used lead sulfide detectors to create an electrical signal when exposed to IR. It was important because it was IR of longer wavelengths than could be detected in photographs. He also discovered that the U.S. was working on similar devices, and at the end of the war, he convinced the U.S. government to release both the German and the American information that they had on these devices. Kuiper realized that infrared detectors could be critical to any kind of astronomy, but particularly to planetary science, because planets glow, in other words, reaching their peak EM emissions well into the IR band. Kuiper was also one of many astronomers. Kuiper was also one of the only astronomers in the West who knew that these IR detectors existed. When he returned to Yerkes, Kuiper began working on adapting lead sulfide detectors to astronomy. And lead sulfide detectors were conveniently sensitive in the near infrared, between 1 and 0.25 nanometers. The near infrared has two key advantages. The gas giants, energy later discovered the atmosphere of Titan, had theorized spectral lines inside that particular band. Also, when you're talking about the near infrared, our Earth's atmosphere tends to be fairly transparent at those wavelengths. Now, it's not perfect, and as I'll talk about in a minute, water plays a big role in that. But there was a chance that you could do it from the ground using those detectors. And with a grant of only $500 now, doesn't seem like much. It was probably a little bit more money than at the end of World War II. He built a very simple spectrometer that could see wavelengths between 1 and 3 nanometers. One thing to think about with these things is because these were fairly large devices, by our standards, they could detect across a fairly decent part of the spectrum, but they only represented one bit or one, what's the word I'm looking for? They only represented one single detector, so you couldn't build up an image that way. You essentially have one big pixel, and that was, it would take them several decades to be able to get the kind of detectors that we have, say, on the Webb telescope, which are more based on electronic detectors as well, but they're a very different technology. The first target was the star Betelgeuse, and his early tests were on the 82-inch telescope at McDonald University, again, run by the University of Chicago and the University of Texas. Kuiper was also an important figure, not the sole figure, in developing the current model of the solar system. He built on work related to the solar nebula hypothesis, which had been put out as early as the 18th century, almost as a guess by Kant and Laplace. But he developed in detail by Carl von Weizsäcker, I'm probably destroying that name, during World War II, and again subsequently read by Kuiper during his intelligence gathering missions. So again, he had special access to information that some of the mainland scientists didn't have because he was pouring through all this information coming through Europe. It's also developed by Henry Norris Russell, Lyman Spitzer, and Subramanian Chandrasekhar, who worked out some of the math, according to a story that I read on his on the boat to Europe from India. That could be apocryphal too, but it is an interesting little detail. Kuiper worked out that forming planets would have no preferential distances from the sun, the forming sun, which basically threw out Bode's rule, and that gravitational instabilities would develop within the nebula. And then the solar nebula would develop into protoplanets, which would then form into planets. There are still parts of this model which are being worked out and which they don't exactly know how they work, even 80, 60, 70 years later, specifically how you get from dust grains up to things a little bit bigger than that. But the basic model was something that he put together from a lot of different research that other folks had already done. He also concluded, and this is the important part, that gravitational instabilities would predict the location of the asteroid belt. And most importantly, based on his gravitational instability models, he speculated that an additional zone of asteroids would be located in the outer solar system beyond the orbit of Neptune. And the zone might possibly be a source of some comets. Jan Oort was also working on the problem of comets and proposed a cloud of objects surrounding the sun and traveling at about 50,000 to 150,000 AU, which is an extraordinary distance. Kuiper's so-called belt was much closer in, just beyond the orbit of Neptune. Comets of periods greater than 200 years approximately were thought to come from the Oort cloud, while comets with periods of less than 200 years and orbiting close to the ecliptic were thought to come to the Kuiper belt. And the important thing is Kuiper only proposed the existence of the Kuiper belt. The actual first object was not identified until the 1990s. Kuiper also did some research on Pluto. He attempted to determine the size and mass of Pluto in the 1940s using the 82-inch scope at McDonald Observatory and the 200-inch Hale telescope at Palomar. And he was, especially because he was interested in comets at that point, interested in Pluto's role in scattering comets in the inner solar system. What he was able to establish with one of the observing chiefs at Palomar with a 200-inch was that a diameter of Pluto of about 600 kilometers, or about half that of Earth. Now, we know today that that was way oversized, but it was important at the time because it ruled out Pluto being an Earth-massed object, which would be required for it to be a major source of disrupting comets and sending them into the inner solar system. Kuiper would then look for a moon of Pluto to help work out the mass of Pluto. He didn't find it. It wouldn't be until 5 years after his death in 1978 that James Christie was able to discover Chiron. The Lunar and Planetary Lab was another major achievement of Kuiper. It originally sprang out of a project to map the moon that was started in 1955. He picked Arizona because of the clear skies, the good weather, and the dry climate. And he quickly became opposed to Edwin Carpenter, the then director of Stewart Observatory, which was a consistent pattern in his career and life. As he tended to get into it with the people he was working with. He didn't get into it with everybody, obviously, but he could be a very taciturn, so he could be a somewhat challenging character to work with, and a lot of people got into it with him over professional differences and some of his character flaws. University President Richard Harville moved the original lab into the Physics and Mathematics and Meteorological building, not now the Physics and Atmospheric Sciences, for anybody who knows our campus well. The lab was started with less than a dozen scientists and just 4 students. Technically, they weren't students of the lab because the lab was not a degree granting department yet. But they did work for the lab. Most of them were grad students. And it was one of the first separate departments and labs of planetary sciences in the country at the time. So why come to the desert? Well, we all kind of get a sense of this today if you know anything about how infrared astronomy works. And remember, at this point, he was very interested in the infrared astronomy of specifically the planets. The answer was water vapor. Kuiper was looking to do infrared observations through his new laboratory, and infrared light is blocked by water vapor in the atmosphere. Having a dry climate and cold, dry mountaintops made southern Arizona an excellent place to do IR astronomy. Atmospheric stability was a factor as well, but when you're doing IR astronomy, the biggest factor is the moisture content. And so both factors played in very nicely because the mountaintops around here tend to have fairly stable atmospheres, but they're also fairly dry. Another factor is they were within the continental United States. So it was close to somewhere that had road access and airport access and things like that. Many of the sites that we use now as outstanding sites are in places like Mauna Kea or the Atacama Desert or even Antarctica, had very limited access at that point, and it was hard to, and for American scientists, and since this was meant to be an American project, that was a huge factor as well. But Kuiper was actually instrumental in establishing the first set of telescopes up on the top of Mauna Kea some years later. So it's not like he wasn't looking for better sites elsewhere on Earth. Kuiper was an expert in spectrometry even before he got into IR research, but his early students also sought out classes in field geology and geochemistry. Here at the University of Arizona. This is after he started the Lunar and Planetary Lab. And then Kennedy's challenge to put a man on the moon and the funding that came with it spurred scientific interest in the moon, and also put out a lot of research money in mapping it. Also, the advances in infrared astronomy started by Kuiper and continued by Frank Lowe and Harold Johnson allowed the first observations of the moon, planets, and asteroids. And many of the devices that were developed here at the University of Arizona were tested on the new telescopes that were being built on Mount Bigelow and continued on the 82-inch telescope on Mount McDonald Observatory. So Kuiper was important, not necessarily the only person doing lunar mapping at this time. NASA needed good maps of the moon to plan for lunar missions. And the first of these to come out under Kuiper was the Orthographic Atlas of the Moon. The source I said didn't give an exact date. It was approximately 1962 that particular edition came out, but it did not satisfy Kuiper. And so Kuiper employed William Hartman, who was the former director of, the Planetary Institute over in somewhere here in Tucson, to project strips of lunar images onto a sphere to produce better maps of limbs. And the rectified lunar atlas was published in 1963. And that was the first to identify the bullseye pattern on Mare Orientale, or at least confirm that it was there. The Kuiper telescope is still in existence. It was NASA agreed to fund the telescope in 1961. This is also known today as the Mount Bigelow telescope, or the big one on Mount Bigelow. There are actually 2 telescopes up there. Financial problems led to the temporary suspensions of construction in 1964. After they worked that out, production continued. Sam Case of the UA Department of Physics crafted the mirrors for the telescope, and the telescope was turned to the moon for the first time in 1965, and photography of the moon was started soon after. The Space Sciences Building, now known as Kuiper Space Sciences Building, was also funded by NASA. It became the home base of the Lunar and Planetary Lab, and eventually named after him, I believe after his departure and death. Kuiper was critical in Project Ranger, which was one of the first probe missions to the moon. Project Ranger ran into a lot of technical problems at the beginning. The probes obviously did not make it because of problems with launchers, problems with the probes themselves, all sorts of things. And in 1963, Kuiper became the chief project scientist on it, which had control over the camera development for these probes. The probes were designed to crash land on the moon and take pictures as they approached the moon that would then be beamed back via radio and television to Earth. Ranger 6 was a failure. Ranger 7 returned pictures of Mare Cognitum. Ranger 8 impacted Mare Tranquillitas. Ranger 9 impacted the crater Alphonsus, and then later, although he wasn't the program director for that, he was at least in the middle of the lunar orbiters projects 1 through 5, which returned images of the whole surface. LPL was involved, but Kuiper was not the project scientist. And then meanwhile, he created the Consolidated Lunar Atlas made with photographs from the 61-inch, which was published in 1967. And that was an important, not the only, but an important part of the lunar mapping that went into making choices about where to land the Apollo projects. One of the main folks that he had controversy with was another scientist who was involved with planetary sciences. He was more on the geochemical and chemical side, which was Harold Urey versus Gerard Kuiper on the hot moon versus the cold moon debate. And this was a debate which took place in the 10-15 years before the Apollo mission started returning large numbers of samples from the moon. Urey, one of the other living planetary astronomers, again, more of a chemist than an astronomer, proposed what was called the cold moon hypothesis, in which the moon assembled from rocky debris and never had a hot molten core or real volcanism on the surface. Kuiper, who had spent time in airplanes and on the surface looking at volcanic fields on Earth, was convinced that the mare had formed from hot volcanic rock that left behind igneous rocks in the hot moon hypothesis. The two argued this over 10 years, and it was not a pleasant argument. They passed papers and journals and things that were not in no means supportive of each other. The matter was finally settled by Apollo samples in Kuiper's favor. In fact, the moon had a molten interior at one point, and the mare were primarily igneous rocks that had erupted from here. And using observations from 9 was able to establish that the lunar surface probably was compact enough to support the weight of a human standing on it. Up until that point, it was actually some scientists had speculated that the lunar surface might be so, for lack of a better term, foamy with dust and loose particles that someone could potentially sink into it. It later supported the Surveyor probes before the Apollo missions happened. So they had a pretty good idea that the scientists were not going to fall into quicksand or whatever you want to call it, or quick dust when they got there. But he was the first one to kind of come up with convincing proof that that was probably the case. And so the missions continued, and they invented the lunar landers and everything else to be able to do that. His later research and discoveries after Ranger, Kuiper continued in an administrative role at LPL. He was critical of bringing the next generation of IR astronomers to Arizona and the Southwest. That included bringing in not necessarily himself, but at least to the reputation of the university, bringing in a lot of the next generation of IR astronomers who worked in the Steward Observatory. So it was not just the Lunar and Planetary Lab that benefited from this. He helped develop Site 2, which is the Mount Lemmon site, into a key IR observatory. He was not exclusively alone in that. Steward was a big player in that as well. But he developed the use of aircraft as bases, or that was one of the projects that occurred under him. I don't want to make it sound like he personally built the airplanes, but he was someone who was involved with that, and that was one of the projects that LPL was working on during a lot of parts of his tenure. Aircraft were the basis of IR telescopes, and with a new generation of spectrometers could look into the IR and produce better spectra. The first case, NASA provided a Convair 990. I believe that there was an accident on the ground with that one, and NASA then later procured a C-141, which was an older version transport plane with a 36-inch telescope. And it was a precursor to the now defunct Sophia, which was flying until last year. Now, the C-141 was retired years ago. That was a much older project. I'm told from scientists I've talked to who were actually flew some of those flights that it was not a comfortable plane to be sitting on. It was cold, it was miserable, but it was a good platform to look at asteroids and comets and things like that with an IR telescope. In 1972, shortly before he retired, the Lunar and Planetary Lab was attached to a new department of planetary science, which is a formal teaching department under the then College of Liberal Arts. So for the first time, they became a major degree granting institution, primarily for graduate students. To this day, they don't have a major program in planetary science. All of their undergraduates are students who are working on minors. And they have, of course, quite a few graduate students working on PhDs, occasionally a master's degree, but mostly on PhD level work. And then retirement and passing. Kuiper retired in 1973, shortly after the founding of the Planetary Sciences Department. He was replaced by Charles Sonnet as the director of LPL and a department head of the planetary science. Within a few months of his retirement, he traveled to Mexico in December of that year to help establish the site of a new observatory that belonged to Mexico. And in December 24, 1973, he had a heart attack in his hotel room in Mexico City and died. So unfortunately, he didn't have much time to enjoy retirement. He passed away within a few months of retiring. And his ashes were placed next to his wife next to the Kuiper telescope on Mount Bigelow. So that was a wall of information. Any questions on any of that?
Yeah, thanks, Stephen. I have one question.
Yeah.
Who operates the Kuiper
telescope? It is originally belonged to the Lunar and Planetary Lab primarily, but today it's primarily run by Steward Observatory. They have joint participation over the telescopes that are under their control of the University of Arizona. It also belongs to, at least some of the time in theory, belongs to ASU and NAU. They all operate that together. I believe the primary user is still the University of Arizona. I was up there this summer with a group, and unfortunately, one of the things that I learned from one of the graduate students who was working there is that it's not terribly subscribed to anymore. Which means that it's not being used all the time anymore. It's used for example, Don McCarthy's astronomy camps, and I think there's still some scientific work being done by graduate students up there. It hasn't been requisitioned largely yet by the Catalina Sky Survey, which runs the 60-inch telescope up on Mount Lemmon, and has not been automated. There's still a CCD camera you can attach to the back of it. But unfortunately, it's because of its size and the fact it's no longer a massive telescope, it's no longer necessarily considered a first-line instrument. But the Steward Observatory, I believe, is responsible for along with LPL and for a lot of the upkeep and maintenance of it. I'm sure ASU and NAU are responsible for some of the budget, but a lot of it is going through us. The cool thing about those scopes is they are exclusively belong to the University of Arizona and Arizona institutions, so we don't have to share them with outside universities like some of the big telescopes that the steward works with, which are shared by a bunch of different institutions. So if you're a grad student looking for some time on a okay sized telescope, you can probably still get time on the Kuiper telescope.
Okay, great. Thank you.
Thanks, Stephen. Good job.
All right.
And the astronomy camp is no longer using that facility.
Okay.
But I wondered, did Kuiper have any children? You may have addressed that, but I don't recall.
I don't think so. I didn't see anything in any of the information I had about any children. He was married. I don't remember the name of his wife. He met her at Harvard University, and while he was a postdoc there, and they were together throughout the rest of their lives, but I don't know about any children.
Thank you.
Thank you very much, Stephen.
All right, no problem.
Now, just gonna switching gears real quick when I find the right button. There we go. Cool. Everyone able to see my screen?
Mhm.
Cool. So continuing on with the night. Sorry, had some warnings. So as I kind of mentioned at the beginning of this session, there are a slew of meteor showers coming up over the next 2.5 months. Kind of using this as a quick primer on what they are, some minor historical things with regards to, sorry, I'm getting office licensing warnings. There you go. With regards to meteor showers, and then we'll go straight to like a list of all the meteor showers that are coming up, and we will wrap up there. So meteor showers are period across multiple nights that see a higher than normal background meteor activity. And all of these meteors generally come from the same or similar portion in the night sky. They typically have an average meteor per hour rate of about 20 or more, which is compared to a normal background-ish rate of about 5 to 7. If you're on a good night, like some of us might have seen out at Tampa, you can get more than that. But typically, excuse me. So like constellations, these meteor showers are, we'll talk about this here in a second, because of how they originate, they're restricted to certain parts of the night sky. So we do have some meteor showers here that are restricted to the northern hemisphere, and some that are restricted or more prominent in the southern hemisphere. Since most of us here live in North America, we'll mostly go through we'll be going through the northern hemisphere meteor showers, although we will touch on some in the south. So one of the I was kind of disappointed when I was looking for this in terms of like, what were there some more historically significant meteor showers, mostly because, people being very religious for and supernatural for much of our history, you would think that, having a giant burst of meteor shower activity would freak a lot of people out. Not unfortunately too much of that in terms of what I was able to find. The earliest knowledge that we have of meteor showers conveniently comes from our good friends in China. They observed there were writings dating to 687 BC, where which we've kind of tied back to what's now known as the Lyrid meteor shower. as one of the earliest records that we've been able to find. The second claim to fame also comes from China with the Perseid meteor shower, which was cataloged in 36 AD. So there's a considerable gap here where I wasn't able to find anything from Greek or Roman records, which was a little bit interesting there that they didn't have anything. So kind of skipping forward quite a bit. The most from there's kind of two conflicting accounts on this, but the term meteor showers were actually dates back with an American, particularly an American surveyor named Andrew Ellicott Douglas, who was tasked by George Washington in 1799 to sort out the border situation in Florida between what was then the very young continental U.S. and Spain, and the Spanish Empire that had predominant control of Florida at the time. I did make this mistake while researching this and was Googling his name to find more information. Do not confuse him with Andrew Ellicott Douglas, who was the founder of the Stewart Observatory in Tucson. They are two different people. I almost made that mistake until I was like, wait a second, this was in the 1900s. This isn't the same person. He was, as I mentioned, on assignment from George Washington, and he was off of doing some navigation work off of the Florida Keys around the time of November. That gets to be kind of important here in a second in terms of identifying the meteor shower. And he was called out on ship during the very late portion of the night. This is an actual quote from his particular journal, where the ship and captains, he was part of the navigation crew using his skills as a surveyor, which were kind of vital to help establish the border. And they had called him out because there was a tremendous volume of meteors and activity all throughout the night sky, which that continued well into the morning, and most of the night sky was just lit up with these meteors for hours. Notice the date here. This is November 12th, 1799, which gets important for one very particular meteor shower, which we'll go into more here in a bit. This was later followed up by what is now known as the Great, that should be Storm, I apologize for the typo, the Great Storm of 1833, which was visible almost exclusively from North America. There are, at least in the levels of activities that were reported, and it was not necessarily seen within Europe's skies. So even with, as we can see kind of suggesting here, is that meteor showers, while they may span multiple nights, may be different depending on your geographic region, even in the same hemisphere. So this particular meteor shower recorded an estimated meteor rate of about 20 meteors per second, which is ridiculous. It would almost be like you're outside of a hailstorm of meteor showers. Given the religious attitudes that were predominant in North America at the turn of the 18th century, many people were coming to believe that the world was ending, which, given the sky situation, quite believable. In order to help placate a lot of the concerns from the general populace, the astronomers at the day had to take a lot more active interest in understanding these events, mostly just to help assure people that Revelations isn't around the corner, we'll be fine. The convenient portion of this is that there are so many observations of these meteors. This is also during the time before photography occurred. We had any photography or night photography of any at all, excuse me. But the sheer number of observations was allowed professional astronomers to identify what's now known as the radiant, which is the portion of the night sky in which meteor showers will appear to originate from. and kind of kicked off what's now known as modern research into meteors. So the majority of all the meteor showers that we currently, well, at least for we as amateur astronomers will be more interested in, originate from comets. A couple of them originate from asteroids, which we'll talk about here later. And the way this works is that comets will cross through the Earth's orbit at or near it. And as the sun is proceeding to melt, the dust and ice on these comets comes to form its tail, this material gets blasted out into space, and it'll linger along the comet's orbital trajectory. So, with given the right orbital orbit of the comet, the Earth will eventually cross into the stream of material, and its gravity will suck it in, and it'll all burn up in the Earth's other atmosphere, and creating the the meteors that we will eventually see. So obviously, this material isn't infinite. It will eventually dissipate over time as the Earth proceeds through the stream. It'll clean it up and loosen it up. So comets that are on their outbound way out that don't return, they might have they're on an escape trajectory. They won't leave anything behind, or they will have already dissipated. Otherwise, excuse me, short period and long period comets will keep renewing themselves as the comet makes a return. Although in some cases, the comets might not return along the same orbital path. So you might still have some situations where the source stream of meteor material would dry up because it would be in a different position that no longer crosses our orbit. This might be if the comet approaches Jupiter, and over time, Jupiter's massive gravity will shift its orbit. And it's kind of a lot of mouthful, and I don't have a really good picture to kind of show that. Nope. So because the path in which the comet mass moves through our orbit doesn't really change, this means that we will cross by meteor showers at roughly the same time every year, give or take a day because of leap years. So this path is also what finding the words here. This because the orbit of every comet is new. This is what changes where a meteor shower will originate from in the night sky with the radiant. And all of the more prominent meteor showers, there are a lot of them. There are over 900 that have actually been officially cataloged, are named by the constellation in which they are predominant from. Of the 900 that the International Astronomy Union has cataloged, there's only about 100 that are like really certain or are distinct, not distinct, predominant, excuse me. I think that's right, yeah. And most of these will have a meteorite, as I mentioned, of about 20 or more. There are a couple that are fewer, but most of those are ones that we aren't really, despite being named meteor showers, doesn't necessarily mean we'll actually get to see them from the ground, mostly because they might burn up in Earth's atmosphere well before they get there. So this kind of gives you an idea of what I've thrown down some terms a lot here of what it's meant by the radiant. I feel like I missed a slide. Did I? Excuse me one second. I had a diagram. I'm not sure where it is. Yeah. Okay, so I hadn't gotten to it yet. So this is a picture showing the radiant of the Perseid meteor shower, and so these bright streaks. over here are the meteor streams that are radiating out from this point here in Perseus. The Perseid meteor shower is one that recurs every year in August, which gets difficult for us here in Tucson because it's always cloudy. But you'll notice that these streaks are originating after the same point. So that just because these picture shows them near the point of the radiant does not necessarily mean that that you should stare at that particular region of the sky, because they would be coming from almost all over, but from this same general direction is what we mean. So like you might be observing some portion of the sky down here off towards the east, but if you follow that meteor's path back, it would wind up here in the Perseid, even if you only saw it visible here at this portion of Cetus. Kind of explain that better. Any questions so far? I know I'm kind of talking pretty fast, and it's kind of a habit, so I apologize if I'm losing some people.
Yeah, Connor, this is Pete. I got one question.
Mhm.
Going back, when you're discussing the comets, short period, long period, whatever the case may be, but all comets in general are going to experience a net loss of mass during their lifetime. Granted, these are long lifetimes. Is that correct?
Yes.
Okay, so there's no way that they're ever going to pick up mass, for instance, going through the asteroid belt or picking up material as they go around the solar system. They're going to have a net loss over a period of time. Oh, Doug's shaking his head.
That can happen, but just from their own gravitational pull. For example, if they move farther out, some of the ice that they were about to blast off as they approach the sun may snap, freeze, and sublimate back into the comet from its gravitational pull. But in general, that's not going to be enough to offset the loss that the comet will experience as it approaches the sun.
Okay, so and as it approaches the sun, I would take it once it gets inside the orbit of the asteroids, that it's probably going to lose most of its material in that zone. Would that be correct?
Percentage.
Yes, but keep in mind this will also be over many orbits, usually.
Oh yeah, no, I
Yeah.
understand. I understand that, but I'm just saying that, in general, comets are going to experience a net loss of mass throughout their lifetime, and granted, that could be, hundreds of thousands, millions of years, whatever the case may be. Although it'd be interesting to see if there is a projected lifetime on any of these comets. And then here again, as they get closer to the sun, that net loss or rate of loss increases in general.
Yeah. So, but on the topic of comet lifetimes, it's one of those things that depends on a variety of factors, such as how big the comet currently is, how close its orbit takes it to the sun. For example, it might be a long period of comet whose orbit never gets inside of the orbit of Venus, in which case it might have a very long lifetime, versus a very massive comet that goes goes more closer in within the orbit of Mercury will evaporate faster because it's being exposed to much more solar radiation.
Also depends on the orbit. If it's even if it gets within the orbit of Venus, if it doesn't spend much time there, it doesn't lose much material.
Okay, and will a given comet change? Are there modifications in its orbit where it could get closer to the sun and maybe on the next time around, gradually move out, or does that change over time? Or could it change?
The orbit usually doesn't change unless it interacts with something else like Jupiter.
Yeah. The primary wings there would be any of the gas giants that would shift its orbit, because you'll have comets that'll go past the orbit of Neptune as well. But Jupiter would probably be the big culprit in shifting any comet orbit, just because it's the big gravity bully here in the solar system.
Okay, thank you.
Mm-hmm. So all meteor showers will have what's known are peak nights. These are the best nights to view a particular meteor shower, but they generally have over but most of the meteor showers that we'll pay attention to typically stick around for at least 2 to 3 weeks, sometimes a little bit more than that. Because of orbital mechanics, which I'll explain here in this diagram that I actually made, because it is a confusing one to try to picture without it. The best viewing times for most meteor showers is anytime after midnight to just before sunrise. Another big thing that we also have to consider when going out to view a meteor shower is where the moon is. If it's a full moon phase, it's generally not worth the effort to get up that early, just because the moon brightness will swamp out any meteors that you might see, with some exceptions. So this showing here, so in the center of the diagram, we have Earth, and the black line is representing the Earth's orbit, with the red line with, so the Earth rotate somewhat counterintuitively. It actually rotates counterclockwise as it goes around the sun. And so with Earth, as it rotates, it's going to twist itself into this meteor stream, so that when we're closer to midnight, which is what would be here if we're on, so we're coming this way. I know you might, let me see, where's, do I have, no. Sorry, trying to, there it is, laser pointer. So Earth is going to go in this direction here. So when nightfall occurs over here on this side, and we're going to, and it's the surface of the Earth is going to slowly twist over into this direction, pushing itself into the meteor stream. I know this is kind of placed off. So when you're over here on this side, you're not going to be in, the meteors are less, they're more likely to skip off the atmosphere, if that makes sense, until you get here where they're just falling straight on it, where you get, where the Earth is being pushed like a boat into the meteor stream. So if you picture this as like a shock front, like as a ship moves through water, with the Earth being the ship, it's going to push itself into this water stream. Does that make sense? I see a couple of nods. So that's in general why the best time to view most meteor showers is when, you ideally as a person are on this side of the Earth, are when the Earth is over here on this side, which happens to be before dawn and midnight. So moving on to all the meteor showers. This one we're kind of in the middle of, actually. It actually peaks tomorrow night. There's actually 2 toward meteor showers back to back. The first one, the progenitor of the northern torrids is the asteroid 2004 TG, which has an orbital period of about 3.5 years. As the name goes, the radiant of this meteor shower is in the constellation Taurus. Thinking about it now, I probably should have tried to grab pictures of where the radiants are within the constellation. But hindsight 2020. The date range of this constellation is from October 20th to December 10th. So you'll be able to see meteors associated with the shower for that entire time period, so almost about 45 days. But the best, thickest part of the stream, which I interpret as also being closest to where the center of the comet's orbit was, which may not necessarily be accurate or true, that's just how I would interpret it, is on November 12th this year. It might fluctuate by plus or minus 1 day, again, depending on the year. It's not a very active meteor shower. In fact, in my opinion, it barely qualifies as one, with the fall rate that has about 4 to 10 meteors per hour. So you might not even notice that you're in a meteor shower with that, unless you knew it was that date. And the fall rate is the anticipated fall rate on the peak nights, by the way. I should clarify that. So for all these upcoming sites, it's on the peak night. These meteors are actually relatively slow amongst the meteor showers. Most meteor showers that you'll see have a velocity of around 25 miles per second, which is very, very fast, upwards about 35,000 miles per hour. For those of us that have the club calendar that buy those, you'll notice that it calls out the torrids as being last weekend. That is actually the peak nights for the southern torrid meteor shower, which is also visible for the northern hemisphere, despite being called the southern torrids. From there, these are these meteor showers are also numbered in ordered from those coming up to those farthest away. So the next meteor shower is the Leonids, which is actually a little bit more of an interesting meteor shower. It comes from Comet 55P Tempel-Tuttle. So the last one was from an asteroid, as we did mention. They do come up from time to time. The reason this meteor shower is a little bit more interesting is because it's prone to very high burst activity. When Tempel-Tuttle returns to our neck of the woods of the solar system, it dramatically changes the amount of meteors that come through this shower. So it goes from a fall rate of 15 to 25 per hour to upwards of 1,000 per hour, or in the case of the 1833 meteor storm, 20 meteors per second. And I do see I have something in the chat. These meteors are actually some of the fastest of the meteor showers that we'll talk about, going upwards of about 40 miles per second. This actually is kind of what makes them a little bit more interesting to observe, because you will see that they do leave very prominent lingering tails in the night sky. They are also, of the meteor showers that I was able to find that did report an average brightness of the meteors, one of the brighter ones, with a often reaching an apparent magnitude of a visible brightness of magnitude -3, which is almost approaching on the brightness of Venus, which is generally magnitude -4.2-ish. So they are very bright meteors when they do get up that high. The peak nights are actually next weekend, on the 17th and the 18th. Which is also nearing a Tempo Star Party night for both of those nights. Well, the 17th is next Thursday. So, and it is also during a third quarter moon. So we could expect, if you're out, at that night, you could expect to see some pretty interesting meteors from this shower. Obviously, the next really big one won't be until Tempel-Tuttle returns, which is slated for sometime in 2031. The last big meteor shower from the Leonids was in 2002. When it actually, so come on. Next slide. There we go. So after the Leonids, we move on over to the Geminids, which come from an asteroid. We actually think that Phaeton might be a comet remnant, or a dead comet, which, Pete, coming back to your question, what would be left over after a comet loses all of its ice? So Phaeton has an orbital period of about 1.4 years. So this string gets replenished somewhat frequently, which also kind of may contribute to its higher levels of activity. So this diagram on the right shows blue would be the orbit of Earth. So while it does look like we should be seeing this meteor shower twice, keep in mind that this orbit is tilted and not really. So only one portion of its orbit passes close enough to Earth. The other might be above or below Earth orbit, and where you won't see a meteor shower from this. It's not easy to tell from the animated image. As its name goes, its radiant is found in the constellation Gemini, and it starts shortly after the time the Leonids end, November 19th, and ends Christmas Eve, with the peak night being around December 14th. This meteor shower, you expect a fall rate of about 120, I was about to say miles per hour with that bullet, fall rate of up to 120 meteors per hour. And the times that I've been out with the Gemini, which have lined up with some other nights in the past, I typically don't see that much. In fact, you might not even see that many at all. So it's one of those things. It keep that up to with a grain of salt. There are, like all meteor showers, various factors that contribute to how much you can see. these meteors are somewhat on the lower end of speeds with a velocity of about 22 miles per second. So, so they will be they are somewhat slower as you see them through the sky. But they also tend to be, from some records, yellowy in color in terms of what the tails. And I'm not quite sure what contributes to the yellowness. What particular element would be the contributor to that there? Questions so far? Okay. From there, we started approaching the Ursids, which this would obviously be a constellation, a meteor shower that you would not be able to see in the southern hemisphere. It comes from comet 8P total, which has an orbital period of about 13.5 years, and we can expect its return for this particular meteor shower in 2035. Despite the name Ursids, it actually comes from Ursa. It actually radiates from Ursa Minor. So a picture of this I saw has the radiant actually in the cup of the Little Dipper. So not necessarily near the pulsar, but it's closer to the cup. It's a very easy meteor shower to even miss. By most accounts, the meteors from this are not very bright at all. Might not necessarily be worth it to go be waiting out in the cold, on the day of the winter solstice here in the northern hemisphere. It's also a very low rate meteor shower, one of the couple that barely qualifies, in my opinion, as being a meteor shower, with only 10 meteors per hour. So while it's there, it might not necessarily be one you would want to go out and look at. From the Ursids, we move on to the Quadrantids. Names always throws me off. This one originates from an asteroid, the asteroid 2003 EH. I do not know what EH would stand for in this particular case, which has an orbital period of about 5.5 years. It is, despite the name Quadrantids, its radiant comes from the constellation Boötes. The original name stems from a defunct constellation, which when the IAU laid out the official constellations in the 1820s, Quadrans Moralis did not make the cut, and instead was given over to Boötes. But the meteor shower has kept its name, so reminding us, of constellations that we now no longer pay attention to in the night sky. This is a deep winter, stemming from December 28th to January 12th, with a peak night shortly after New Year's, of all places, on January 3rd, which is approaching a first quarter moon for us this year. So one of the it's one of the meteor showers that could be highly variable. I'm not quite sure what contributes to the variability. I would assume, it might have higher peak nights once Astro 2003 EH is making its return. I'm not quite sure how close we are to the next return. I forgot to put it on this slide, so I apologize for that. Also, kind of more on the low end for speeds, with an average meteor velocity of about 25 miles per second. Some of the NASA resources consider this a difficult to view meteor shower, mostly because a lot of places in the continental US are very cloudy that time of year. And it's also typically very cold, and people don't want to go out in the cold. So they consider this a more difficult to view meteor shower. But if you can, if it is one of those good years, it is a very spectacular one to go out and look at. From there, we move on to the Lyrids, and I think I have 4 more meteor showers to go after this, so we are almost done. With the Lyrids, which we trace back to comet 1861 Thatcher, which is a very long period comet. It has an orbital period of 415 years. So don't hold your breath waiting for this one to come back. It is slated to come back in the late 2200s. I'm pretty sure I won't be alive at that particular point. The radiant originates in the constellation Lyra. It is a good spring meteor shower, typically visible between April 15th to the 29th, with peak nights around the 21st and the 22nd. Considering that we do have records of the constellation, not the constellation, of this meteor shower going back, all the way to the Chinese, it is one that you would probably want to go out and see. It does typically be a fairly consistent producer of a good meteor shower. When it does, this is also can be one of those highly variable meteor showers, with some records being reported of up to 100 meteors per hour. But the more typical that you would expect to see is 10 to 20. What's interesting is that NASA notes that unlike most other meteor showers, which you would want not, when you're looking at a meteor shower, you don't want to observe close to the radiant, especially because the radiant is usually rising in the night sky at that time. It's actually best to look away from the radiant and other portions of the sky, but just kind of keep your eye peeled that I need to look, if I see a meteor originating from this particular direction in the sky, it's probably a Lyrid. So approaching a little bit higher on our speed charts here, with most of these meteors approaching about 30 miles per second as they re-enter our atmosphere. And then after the Lyrids, we have the first meteor shower that comes from Halley's Comet. The Eta Aquariids, which originate in the constellation Aquarius, also kind of overlapping a little bit with the Lyrids there. So the other reason you also want to pay attention to the radiant is because you might be seeing on some nights meteors that come from two different meteor showers at the same time, because as we see here, this one does overlap. Some of these do overlap with each other, excuse me. So with Lyrids from the 15th to the 29th, and the Aquariids also from the 15th but to May 27th. So paying attention to where you're seeing these does help you indicate, which meteor shower that meteor might be associated to. They have Aquarius typically have a fall rate of about 10 to 30 per hour, with the higher end of the fall rate being visible from the southern hemisphere. This meteor shower happens kind of low in the sky, even from Tucson, so it's mostly closer to the horizon. So the radiant is closer to the horizon than it would be from if it was farther up, closer to us. These are like the lead. These are very fast meteors, approaching about 44 miles per second, and commonly have meteors that will leave a tail lasting anywhere from several seconds up to several minutes. And so looking more closer to the horizon for us, since we're here in the northern hemisphere for this one. From there, we move over to the Delta Aquariids. We actually haven't identified the progenitor comet for this particular meteor shower. We suspect it's what's cataloged as Comet 96P Mach-Holes, but it's contested. They haven't quite confirmed that one. It's a short period comet, returning to the inner solar system every 5.3 years. So it actually will return next year in January. So the meteor shower for the Delta Aquariids next July, unfortunately it's monsoon season for us, so we might not see much here in Tucson. But elsewhere, it might be a little bit more spectacular to see, given the comet's return, if it is indeed the source. The low end of the meteor fall rates of about 20 meters per hour. Also on the slow wind of about 25 miles per second. Despite, I forgot to mention there are two Delta Aquariid meteor showers, a northern and a southern one. So this was cataloged as the southern Delta Aquariids, but even though it's cataloged as southern, that's not necessarily associated to our southern hemisphere. It's just of the two, it's the more southerly meteor showers that radiate from Aquarius. Unfortunately, even with some of these characteristics, the meteors typically are somewhat faint to see. At least for us here in the northern hemisphere. And two more slides left. Moving on, we move on to the big boy meteor shower. The first is probably one of the ones that many people have heard of. It is the meteor shower that has the largest fall rate of all the typical meteor showers that we can see, with the exception of the Leonids when its progenitor comet returns. It originates in the constellation Perseus and is a southern meteor shower. Summer, excuse me. Its peak rate is every August of around 11th through the 13th. This year it's the 12th and the 13th. Unfortunately, the times that I've tried to view this one, it usually ends up poorly because it typically catches the first quarter moon, or in some cases even the full moon. So, but if you're lucky, and it's also not monsoon season, like it is for us, it is one of the more spectacular meteor showers to go see, with up to 200 meteors per hour. Although most of the time, 50 to 100 would be a more typical number that you could see, at least from a semi-dark sky like you might get around Tucson, unless you're out at like CAC or something, or a dark sky site. The meteors from the Perseus are actually relatively fast, coming in at around 37 miles per second. And like the Leonids, they do share a strong, prominent tails and a very high apparent brightness of also approaching magnitude -3. So it is one of those where a lot of people will try to go out and photograph this particular meteor shower, just because it is one of the more active ones that we can see. And last, we wind up with the Orionids, which is a meteor shower that ended here in October. So unfortunately, if you didn't go out, you did miss this one, and you will have to wait till next year. This is the last meteor shower that we'll talk about, and this is the other one that comes from Halley's Comet. To give it its name, it does come from the constellation Orion, and it runs from late September to late November, with a peak night of October 21st. So it's almost, you would say, a Halloween meteor shower. These are actually some of the slowest meteors, with I completely read my own slides. It has a fall rate of about 15 meters per hour. And I believe, Stephen, given that bright one that I saw when I was out with you at Temple last month, that one was one of the Orionids, which left a very beautiful, really thick, lingering green tail across the night sky for about 4 seconds before it disappeared for us last month. And they're also on the very high end of meteor speed, with a fall velocity of about 41 miles per second. So they do go by pretty quick. And that wraps up this. I hope you guys have at least a couple of things to go look forward to with meteor showers here over the next 2 months. Any questions, comments?
Thank you, Connor.
Cool. Yes, Doug?
Okay, so you in your lecture, you said you didn't know why the meteor showers had variable rates, and I can explain that. So as the parent body is in its orbit, and as it's getting closer to the sun, and the dust particles are getting blasted off by the solar wind and going in the orbit, that process is not even. You get clumps of material, places where the particle stream behind the parent object is more dense than other places, because it just doesn't happen evenly. If you look at the tail of comets, in particular, if you study the dust part of the tail of comets, you'll see clumps in the tail, places where the tail is more dense than other places, and that's increased density in the particles. And that's, you'll see the same thing in the meteor showers. We'll go through a dense part of this stream, you get a higher rate of meteors than when you go through a less dense part. And typically, the other thing that you should keep in mind with the peak rates for these meteor showers, those peak rates oftentimes only last a few hours.
Thanks, Doug. Cool. And with that, I'm gonna stop the share and check some stuff. Cool. And with that, that actually ends for the night. Thanks, everybody. Doug, Stephen, Pete, we'll talk with you guys a little bit to see if we can figure out if we should cancel or next month's meeting or not. So I don't actually have any as usual. I don't have any topics lined up for December at this point. Not even quite sure.
Well, I had missed the October session because I was too tied up in my fundamentals class. I couldn't help out. But I would be willing to do a